first section of today's classwork assignment, you're asked to locate the absolute extremas of a function on a closed interval. Let's look at question number 28 as an example. Now recall that in order to find your extrema values, your very first step is that you need to find the critical numbers. Now remember, to find the critical numbers are the numbers of the x values at which the derivative is equal to 0 or the derivative does not exist, as long as that value where it does not exist is in the domain of the original function. So first we need to find the derivative of f of x. So we will need to do the quotient rule. Low d high minus high d low over low squared. Perform some algebra and simplify this down, and we'll end up with our final answer as the derivative of f of x is equal to negative 2x squared plus 2 all over x squared plus 1 quantity squared. Remember, a fraction is equal to 0 when the numerator is equal to 0, so we will first set the numerator, negative 2x squared plus 2, equal to 0, and solve this little equation, and we will end up that we would get x is equal to either plus or minus 1. Next, we need to look at when the derivative is undefined. Well, the derivative is undefined, in this case of a fraction, when the denominator will equal 0. So we ask ourselves, when can x squared plus 1 quantity squared equal 0? Well, that can never happen. So that means we only have two critical values in this problem, and that is negative 1 and positive 1. Step 2 is, now that we have the critical values, we need to check into the original function value of the endpoints and the critical numbers to figure out which will give us our absolute maximum or absolute minimum for the problem. The best way to show you work for this step is to make a t-table in which you list your endpoints and critical values in increasing order. And then we're going to show our work on substituting in each x value into our original function to figure out the function value at that point, or the y value. So in this case, I have the endpoints and critical values of negative 2, negative 1, 1, and 2. So first I will plug in negative 2 into the original function value and simplify it down. And we find at negative 2, our function value is negative 5/4. Repeating this process for negative 1, 1, and 2, end up with the following points of interest: negative 1, the 0.11, and then the 0.24. Looking at our table and our y values, we can easily see that negative 1 is a minimum number and 1 is a maximum number. So to translate this into our answer for question number 28, we would write the following. The absolute maximum is 1, and this occurs at the 0.11. And the absolute minimum is the value negative 1, and this occurs at the point on the graph of negative 1, negative 1. Look at another example in this section, which is question number 36. So we're going to start the same way. First thing we need to do is find the critical numbers by finding the derivative of our function. In this case, that will be 2x plus sine of x. Now, to find the critical numbers, we set the derivative equal to 0, since we don't have to worry about when it does not exist, because 2x always exists and sine of x always exists for all values of x. So all we have to do is figure out when it's equal to 0. Solving this equation, we end up with negative 2x is equal to sine of x. And now this is a little bit hard to figure out. We don't know how to get this x equals implicitly. So we need to look at some of our knowledge that we know of our graphs of these two functions. Now remember, when you have two functions equal to each other, graphically, the solution to that will be where those two functions intersect each other. So we're going to graph negative 2x in one color on this graph here, and then I'm going to graph sine of x on the other in another color. And what we're going to be looking for is, when does sine of x intersect with the graph of negative 2x? So for y2 sine of x, I'm just going to plug in a few points here in my domain of negative 1 to 3. In blue, I'm going to graph the equation y equals sine of x. Now, since this is a trig function, we've memorized some of our sine graph by the radian measurements, pi over 2, pi, 3 pi over 2, etc. Let's translate those into decimal values so that we can easily plot them on this graph. Now I'm just going to plot each of these points. Sine of 0 is 0. Sine of pi over 2 is 1. We know sine of pi is 0. Sine of 3 pi over 2 is negative 1. And sine of 2 pi is 0. Now let's go back a little bit so I can get to that negative 1 in our domain. We know sine of negative pi over 2 is negative 1, and sine of pi is 0. And this is what our sine curve looks like. Now from our graph, it's easy to see that we only have one point where the blue graph intersects the green graph, and that is at the point 0, 0. So that is the only solution to this derivative. So we would say x is equal to 0. Remember, step 2, when we're trying to find the absolute extremas on a closed interval, is now we need to test our critical number, which is 0, and our endpoints of negative 1 and 3 into the original function to determine which one gives us the largest and the smallest value. So we will set up our t-table again with our x values of negative 1, 0, and 3. Then we will plug in our y values into our original function, y equals x squared minus 2 minus cosine of x, and simplify it down and figure out our y values for each function. At this point, I'd like to make an important note about using your calculator. Since sine of negative 1 is not one of those set angles that we have memorized, you may use your calculator and plug that into that in order to get this decimal value. But on the other hand, since cosine of 0 is an angle that you have memorized, you must give me the exact answer for that problem. So again, anytime you're working with these trig functions, if the angle given to you is any of the angles that we know the exact measure for, such as 0, pi over 6, pi over 4, pi over 3, pi over 2, or any of those equations that have those angles as reference angles, I need exact radical answers, not decimals. But if the number that you're plugging in is not one of those angles, or the angles who has those angles as reference angles, you may use your calculator and give me the decimal to 3 decimal places. Remember, unless otherwise specified, we always use radian measurements in this class, so make sure your calculator is set on radian mode. So for this example, we have the critical numbers of negative 1 has a value of negative 1.540. Critical number of 0 has a value of negative 3, and the critical number of 3 has a value of 7.990. So we have a minimum at negative 3 and a maximum at 7.990. So our answer to this problem would be our absolute maximum of 7.990 occurs at the point 3, 7.990. Our absolute minimum of negative 3 occurs at 0, negative 3. 3, we're going to locate the absolute maximum extrema over different intervals. So for part A, we're going to find it for the closed interval 1 to 4. So first thing we do is we find our derivative of f of x. But this case, 0 can never equal negative 1, so we have no critical values for our function. So in our t-table, we're only going to have our endpoints of 1 and 4. And we plug in 1 into the original function of 5 minus x, we end up with 4. Plug 4 into the original function, we end up with a value of 1. So 4 is a max, 1 is a min. For part A, on the closed interval from 1 to 4, we have an absolute maximum of 4 at the point 1, 4. And we have an absolute minimum of 1 at the point 4, 1. Now for example B, we have a semi-closed interval. It's closed at 1 but open at 4. So that means that the endpoint 4 is not included in the domain of our function. So it cannot have an absolute maximum minimum at that point. So in this case, we have an absolute maximum of 4 at the point 1, 4, but because 4 is not included in our interval, we have no absolute minimum value. Part C, this time 1 is not included in our interval, so we will not have any absolute maximums, but we will still have our absolute minimum of 1 at the point 4, 1, since 4 is included in our closed interval. In part D, 1 and 4, neither 1 or 4 are included in our interval, so those endpoints are not included, so this one has no absolute max and no absolute min. Let's look at example 40. We have f of x is equal to the square root of 4 minus x squared. So we're going to start by finding the derivative of this function. Now remember, when you do this derivative, don't forget to do your chain rule and multiply by the derivative of the inside, which is negative 2x. Simplifying this down, we end up our derivative as negative x divided by the square root of 4 minus x squared. Now, this will occur when the numerator is equal to 0, my derivative will be 0, and when the denominator equals 0, my derivative will be undefined. So I get that my derivative is undefined at x equals plus or minus 2. So I need to check and make sure plus or minus 2 is in the domain of my original function. Yes, I can take the square root of 0, so 2 and negative 2 are in the domain of my original function. And so I have 3 critical values, and now my endpoints are luckily one of my critical values of negative 2 and 2. So all I have to do is check negative 2, 0, and 2, plugging that into our original function to find the y value of each. We end up with function values of negative 2, 0, 0, 2, and 2, 0. So let's look at A. We have a closed interval from negative 2 to 2, so that means we do have an absolute minimum of 0. But this absolute minimum occurs at 2 points. It's okay for it to occur at multiple points, but our absolute minimum value is only the 0. Our absolute maximum is 2, and that occurs at the point 0, 2. For B, we have a semi-closed interval at negative 2 and 0, not including the 0. So in that case, we have an absolute minimum of 0 at the point negative 2, 0, but there will be no absolute maximum since the point 0, x value 0 is not in the domain of the function. Part C, we have a open interval from negative 2 to 2, so therefore we cannot include our negative 2 in there, so we have no absolute minimums, but we do have an absolute maximum of 2 at the point 0, 2. In part D, we have a semi-open interval from 1 to 2, including the 1. So in this case, we cannot include 2, we cannot include 0, and we cannot include negative 2. So in that case, we have no absolute maximum or no absolute minimums to this problem. For our last example problem today, let's look at problem number 42. We're asked to sketch the graph of the function to look at the graph to locate our absolute maximum minimum. So this is piecewise function. So remember, I'm going to graph the linear function 2x plus 2 from 0 to 1. So this will be this straight line here in blue. Now, in green, I'm going to graph the parabola 4x squared from 0 to 3. So from 1 to 3. So at 1, I plug it into that equation, I get 4, so I got an open circle at 1, 4. Plugging 2 in, I get 16. Plugging 3 in, I get 36. Connecting those 3 dots in my parabola curve. And these two put together is my function f of x. So it's very obvious from my graph that I have a max and I have a min. So you can see I have a maximum value at the point 336. So 36 are a maximum. And I have a minimum value of 2 that occurs at the point 0, 2. So let's write that as our answer. Absolute minimum absolute minimum of 2 at the point 0, 2, and absolute maximum of 36 at the point 336.